Well, welcome back. The next speaker is Beverley McKeon, professor in mechanical engineering at Stanford, and she's going to talk about what makes turbulence tick. Beverley?
Thank you, Luca. Thank you for the invitation to participate. I'll start my talk with two warnings. So first of all, this is going to be a lot less sophisticated than anything that you've heard thus far. The second is, if you wanted to hear the answer, I don't have it, but I'm working towards it. So I'm going to motivate what I'm going to talk about with the problem that interests me most, which is understanding the dynamics of turbulence and wall turbulence in particular. I should say, I was just talking with Roger, I'm an engineer by training and worse than that, an experimentalist. So these are tools towards an end, and hopefully you'll see what that end is. This work, it will be dominated by work done with Benjamin Herman from the University of Chile, Peter Badu, who sadly passed away a couple of months ago, who was an instructor at MIT. Yeah, very sad. Peter Badu, I last saw him in person here, actually, at the last time I was at the Isaac Newton Institute. And then Steve Brunton. So this is a collaborative group that has moved there. We've worked together on some of these topics. Richard Seaman and Nathan Cutts will appear on one of the papers. And if I get to examples at the end, Raoul Arun, who's a graduate student at Caltech, and Yuting Wang, also a graduate student at Caltech, will appear. The work is supported by the AFOSR and Vannevar Bush Faculty Fellowship through the ONR, which is a great freedom to explore some of these kinds of topics. So if we're advancing, yeah. So here's sort of the essence of why thinking about wall turbulence in this particular way. I've used this slide many times before. If you move from the left to the right, are people going to see this if I use this? Well, no, because it's got no batteries. Okay, fine. There, right. So on the left, we're going to focus on incompressible flows here, not because the methods fail elsewhere, but that's a topic of particular interest. So on the left is the DNS over a flat plate from Wu and Moyne, and this is a visualization. You can think of it for the non-turbulence expert as connected vorticity. So vortical structure with some coherence in space and time. There's a lot going on that could be called a forest of hairpins, because the elemental unit is similar to a hairpin, and you can see that in this reduced basis obtained from observations in a flow, together with some inspired intuition from Townsend going back to Cambridge, going back to the 50s into the 60s. So this is a unit that's within that hairpin forest. You can see that these yellow structures are sort of hairpin shaped in average, so they reach up from the wall and down again on the other side, but you see partial structures. You rarely see that full, complete loop. You can see that there's a spatial preferential organization. These blue blobs show low momentum, so the sense of rotation of these yellow ones is fast over the top, slow between the legs. And then there's a chicken and egg question as to whether you see the low speed blobs here, or the regions of low speed or low momentum, because the hairpins gathered in that way, or whether the blobs aligned the hairpins. If you think about this sense of rotation, it could be either way. So from inspiration and observation, Adrian et al. Put forward this model of the elemental unit. And so if we go a little further, this is the sort of prediction we can get from the Navier-Stokes equations for those units, and this is a three-mode prediction from a resolvent analysis. So as you've heard in various ways thus far, we're seeking sparse representations in the right basis. And so hopefully what I'm showing you there is that there is some structure in this very high dimensional system. So my laptop is not jet lagged and actually gets there. Here's the outline. So I think I was probably invited to talk about things related to resolvent analysis, because that's what I do a lot of. So what I want to do is review this particular approach, both the operator and data-driven version of this, or at least the things you can do with regards to using the linear operators. And I'm going to talk about three developments So one is learning the resolvent, the linearized operator from data, in the case that you didn't know the equations of motion. I'm going to talk about how one might put in some physics-informed constraints, bearing in mind that this is already physics-informed in the sense that we're working from this linearized operator. And then I'm going to talk about disambiguating the linear and the nonlinear pieces to fit into this particular structure that I'm going to talk about. And if I have time, I'll give you a couple of examples of things that we've been able to observe and do based on this kind of structure. So, it's taking a long time to switch over, but here we go. So our approach, we're going to think about this dual type of approach. We think about, on the right-hand side, spectral POD. So if I go into the data and I look for what are the most energetic modes, parameterized in some way, and here we're going to use this parameterization at the bottom. I'm going to think about turbulent channel flow. So with homogeneity and stationarity, I can Fourier decompose in X, streamwise, Z, spanwise, and in time. And so these are some SPOD modes from Abreu et al. From a pipe. And red and blue is showing the plus or minus modes relative to the mean. So that's the data-driven version of extracting modes. Over on the left-hand side, what we call resolvent analysis. It has a long, long history, and Peter and Clinton Henningsen, a discussion about this for transitional flows. We use the resolvent linearized operator to understand what modes are naturally amplified by the system. And they're amplified in a forced sense, so we're talking about the pseudospectra rather than the eigenspectra. But that will give us another way to get a basis set, and the mode shapes is a slightly different view of a channel, but with some similarity. This is a hierarchical set of modes, some similarity to the ones you see from the pipe on the right. They're not the same, and I'll tell you why in a moment. But then you can also see you can reproduce these kind of hairpin structures that I showed you before. So to be clear, we've done a lot of work on the left-hand column here. The right-hand side has been advanced tremendously by my former colleague, Tim Colonius, Aaron Town, and they would give you a very nice talk about data-driven stuff going down the right-hand column and how it crosses over to the left. I'll show you a little bit about that crossover, but they really tie things together very nicely. So here's the outline of what we're trying to do. If we take our instantaneous field and we divide it up into some mean, so basically I'm not going to be too specific about it right now, but we've just averaged out the time dependency. There may be some further reductions in the channel, for example. This will only be a function of normal distance, and we'll retain the fluctuations over here. And then we write the system in terms of the linear dynamics relative to our turbulent mean. And the novelty of anything here is that instead of trying to understand what the forcing is, I'm going to give up with the cursor, instead of trying to understand what the forcing is, that input F is, we're going to say, well, we actually know what that is. That is the nonlinear term. And so it becomes a modeling. Great. So we actually know what gives the closure. It's the nonlinear term. And so the question is, how far can we advance knowing that and modeling? And so there's a lot of work being done on the linear dynamics for laminar, transitional, and for turbulent flows. But we want to tackle this whole thing. And so the piece of information here about what makes turbulence tick is this. That's the thing that's going to sustain the otherwise linear dynamics. It's going to move the energy around in wave number space. So for each of these parameter sets, we can write the transfer function relationship between u at that set of wave numbers and frequencies and the input forcing here, and this then is the resolvent. The benefit of this is now we can have a reduced representation already in this wave number frequency space. So if you think of this as a cube where the filled circles, filled dots tell you that there is a non-zero amplitude, we already can constrain this cube because we know that for turbulent motions is very little energy, or perhaps even zero energy, for things that convex slower than about 5 viscous units, 5 meter, and for the incompressible case, anyway less than the maximum velocity in the domain. So there's a wedge in here that we could already say constrains the activity, and then can we find some sparsity in there as well? There's, right. So then the way that we proceed in terms of analyzing the linear dynamics here is through the SVD in the usual way. And so now we have an H operating on the right singular mode. These will give us sigma, the gain, times the left singular modes, the response mode, which is called the size. They're orthonormal set and they're ranked by the singular value. One more, or two more, I think, pieces of information. So if I had a complete representation here, in terms of the modal basis coming out on the left-hand side of the linear dynamics, I could expand my velocity or velocity and pressure field in terms of that pressure. I could expand my response field with a weighting, high bar here, and also the forcing field. So once I have these basis sets through the SVD, I could write expressions, and I could work out what the interactions are, or how important the interactions are. If I call the velocity weights chi, so that would be a sigma times chi bar. For each resolvent mode, I can work out the interaction term, the projection onto the forcing mode, velocity weights here, and that would be somewhere relevant. So in theory, at least, I could close this loop. Of course, in practice, that's not compact because we haven't found the forcing in its most efficient way, and we haven't talked about how to actually determine those weights. One more thing that we need to know here is that there is another simplification, which is that if we're thinking about just the velocity, which often we are, not always, then the only bit of the forcing that does the damage is the solenoidal part. So anything else can be absorbed into the pressure. So that's not usually what we calculate, but there is a simplification there. So in terms of data, I haven't really done anything very much. This is all analytical. Where the data piece enters before we go any further is that the mean profile, the turbulent mean, is an input throughout all of this. So we assume that we knew that here. And therefore, anything we've learned about the turbulent mean is actually impressed into that operator. So here's an example of the mean velocity profile for a channel flow, distance in the wall in viscous units. This is the mean velocity for the channel. So we know even as you go up in Reynolds number, this bit, the inner region stays the same up to a y plus of about 100. We could argue about that inner limit, but about that. There's a self-similar region. That self-similar region will grow in y plus with a fixed outer limit in y normalized on the channel half height as we go up in Reynolds number, and then there's a wake region, which is about 90% of the channel. So that self-similarity is passed to the resolvent operator, and in fact we can extract the scalings now, both in inner and self-similar scalings. So the operator itself, the resolvent, becomes self-similar under these representations here. I've omitted the outer one because it turns out that the scaling, Reynolds number scaling, is not amenable to the thing not blowing up as you go up in Reynolds number, so we have to sort of suppress those. Okay, so moving on, this really nice connection was brought out by, in the town, Schmidt with a T, that should be Encolonius, that's Oliver Schmidt, the connection between S-pod and resolvent modes. So the S-pod is done on the cross-spectral density. So you take the correlation, one takes the correlation matrix, takes the Fourier transform of that, extracts a single frequency mode, that's a single frequency information, and then looks at the decomposition, the POD decomposition of that. You can relate the statistics of the response, the velocity state, and the statistics of the forcing through the resolvent. So this is now the resolvent from before. Just change to a Q here to agree with the terminology there. And if the forcing is uncorrelated, so if the statistics of SFF are a scaled version of the identity, then you can see that the SCON modes will be equivalent to resolvent modes, because that SFX has gone away. So that's good in the sense that the data-driven and the operator-driven modes would give you the same example if there were no structure to the true forcing. But of course, there is structure to the forcing. And so the question we have now is where do we want to take our modeling? Do we want to go down the operator version knowing that it's not giving us the truth, or do we want to go down, or the exact truth? We want to go down the data-driven one knowing that we have to have full state or some state information. So that's a choice. In terms of extrapolation, one could think about modeling in either way. But what I want to draw our attention to here is that if we're going to use either of these approaches, we need to know that H. Okay? So either we need to know our governing equation, or we need to be able to find it. So can we obtain the resolvent from experiment? Let's assume we didn't know our Navier-Stokes equations. Can we find that linear operator that will give us the behavior we were just showing before? And so the answer is yes. In this paper authored, lead authored by Benjamin, we adapted basically a technique that exists for learning the eigenspectrum to learn the pseudospectral information. So one collects state snapshots for a transient. So we see this is for a channel flow. We see the channel flow with some disturbance, we watch it evolve and decay, and we do that for multiple initial conditions. And I'll come back to what those are. Sorry?
What are the structures?
Oh, this is an isosurface of, I can't remember, this is electricity velocity. But yeah, so there's a different initial condition perturbation. We do it over and over, and the key is going to be how much of the space we span with those conditions.
And you let it go steady state?
Yeah, so we let it evolve. So I should say, I'm sorry, I didn't say it at the beginning. So this is transitional flow, channel flow. So we're not fully turbulent yet. These are going to be small perturbations, but they are going to decay away. Right? So they evolve and then decay. But I'll tell you why we do that and how we solve that as we go forward. So we assemble the data matrices as if we were about to do a DMD, because we actually are going to do that. And then we get to an approximate eigen decomposition using the DMD approach based on the same shifted data sets as usual. So now we can build a projected resolvent based on this eigen representation shown here. And we will be able to scan over frequencies now to get, rather than the frequency by frequency information, we can get the the singular value, the resolvent norm, the sigma 1 over all frequencies here. So once we've done that, we can now synthesize back our size, phase and size, our forcing and response mode, and they will have some representation as shown here. So this is what the sample of a wall normal and streamwise velocity would look like. And so I want to make sure I'm clear that the method of recovering the eigenspectrum is not novel. The piece here that we've added on is to get back to the resolvent. And so here are some references that speak to various parts of that. The examples or the results that I'm going to go on to show are associated, as I said, with the channel flow. So here we are. So the way this proceeded was the results here. We took 15 random disturbances, and we can regenerate now the spectrum, so the resolvent norm showing sigma 1, and we can capture the eigenvalues as shown there. There's the optimal forcing and the streamwise velocity, and those are in agreement with what we would get from knowing the operator. So you can see that from the fact that, bless you, that the data-driven version is in blue, and the operator version is the gray. So we've captured a lot of what's going on, or the important stuff. The next thing we did was excite just the optimal forcing. So we said, well, we know what it should be in each case. So in this central case here, we put in the optimal forcing, and then we only capture what's happening at that frequency. but we capture it very well, right? So we put in the optimal forcing and we get back the optimal response. And so the final thing to say is, well, what if we put in a localized impulse, so something that would be much more practical to do in a real flow? And so now we do pretty well at capturing some of the optimal, but you can see that we're missing quite a bit of what is going on. And you can see that the projected modes also have localization in them. So why is that? Well, you can actually work through and show that what we're getting is the projection of the resolvent. You just trace through the C and D operators up here. This is what we should be getting, and this is the projecting version of the resolvent mode. So this is for the impulse. This is this case, right? So if I took, so what we're showing here is that if I took the full resolvent, but I did the projection associated with what I put in, I would get this, which is the same as this. So I'm learning all that I could from what I put in. So the question earlier about what are we putting in is, well, it depends on what you want to learn, but it's only as good as what you put in, as is often the case. Okay, so we were pleased to see that we could do this, and we thought that, well, this might be useful for systems where the governing equations are not known, and it would bring to bear some of the machinery that various people have been putting forward in the context of resolvent analysis. And or allow us to do some compression in terms of what is important for given flow scenarios. It inherits its capabilities and limitations from DMD. And we have to figure out how to efficiently explore the state space. The fundamental limitation here is about the linearity of the model. So I deliberately used a case with very small perturbations and in a transitional flow, because through the DMD we're doing a linear fit to what is going on. So we are trying to do the left-hand side of this picture at the bottom, and we got away with it because the perturbations were small in this scenario. I'll say one more thing about this linear case first of all, but briefly. We also thought about what were we asking the DMD to do relative to structure that we already knew about in the data. And so again, Peter was able to construct pi DMD, physics-informed dynamic mode decomposition. And so if you think about ways one might do physics-informed learning, you might think about augmenting the data that you're taking in, putting some loss functions, or else applying constraints actually in the learning. And so this is one of the latter approaches. So now when we do the minimization associated with DMD, we actually put the constraint there so that we are constrained to lie on the matrix manifold representing the structure of the data. And by that I mean something like shift invariance, some symmetry, some causality, depending on the problem that you're trying to look at. I'm going to give you an example where we have shift invariance. So that's embedded in the actual minimization. So here's an example with linearized channel flow again. We're going to do the localized disturbance as we did in the last example before. And this time we're asking the DMD to work with this shift invariance that we know is there. And so what you see at the top is the initial condition. We monitor the transient and the decay. And now in A, we are embedding some structure. I'm not going to go into a massive amount of detail, but the thing that you need to see is that this is the learned spectrum where the gray is the truth again, the red is what we get from regular DMD, and the blue is what we get from pi DMD. So we've just embedded something that we knew about the data in there, and rather than asking the DMD to learn it, we've encoded that. So we could put those two pieces together. But more importantly, to get to turbulent flows, we need to be able to disambiguate the non-linearity. So if you know what that is, and Benjamin has sort of run this through, if you subtract the nonlinear terms, data-driven resolvent analysis will work just fine, but of course we don't necessarily know them. So can we learn the nonlinear terms? And the approach we came up with is Lando, short for linear and nonlinear disambiguation optimization. So we'll start with this model up at the top. So we've got the linear operator, just rewritten from the Resolvent formulation I said. We've got a linear operator L, and then the non-linearity in N. And so once again, we collect our data pairs, so our X's and Y's shifted in time. We're going to put them into that same DMD structure, or like shift structure here. But now we're going to define a kernel function. So we get to choose which form we would like for that kernel. The Gaussian is the workhorse. Of course, we know that we're looking for a quadratic in this in the Navier-Stokes, the incompressible Navier-Stokes example. But we get to choose what kernel function we apply, and then we build our sparse dictionary. I'll talk a little bit more about this in a moment, but basically in terms of the kernel, we're trying to learn in a compressed setting, so lift to a compressed setting, and then we're only trying to learn when our data tells us something new. So that's the dictionary piece. So then we can perform regression subject to that minimization on the bottom there, and then we can extract the model. So in schematic, at least, we now have the nonlinear forcing on the top right here, and we've learned the linear operator correctly. And then we can choose what to do from there. So just to go back through the kernel methods, maybe those are well known in this context, but here's a very simple example that Peter put together. So if we have data, we've got x1, x2, and x3, and the quadratic is known to be nonlinear. Sorry, the nonlinearity is known to be quadratic. We could use something like SIMD, where we explicitly put in these permutations. If we're interested, as we often are, in obtaining an inner product, one can count up, and that would incur 23 operations. If we slightly modify the groups that we look at to this slide down here, so all we've really done is put in some scalings here, but this can be written explicitly in terms of inner product dx and x prime. So we've allowed this to be compressed. To calculate that would require 6 operations, and we never had to store this feature space that we were talking about before. So we're going to try and use the kernels, and then going to use this dictionary-based idea as well. So if we had an explicit model like SIMD, we would be working with this kind of data structure, get unmanageable very quickly as this dimension vector grew. If we're working with an implicit kernel method, reducing our would be down to n by m, so kernels approach to reduce the space of what we're looking at. But we're going to be able to reduce it further by only updating, again, in our dictionary when we learn something new. So some results, we went through various systems here. And so a lot going on. There's 4 examples over here. This is what we would learn from DMD on the full nonlinear system, so in schematic once again. This is what the exact linear part is known in the equations a priori, and this is what would be extracted in terms of the linear part using the Lando, or what is extracted using Lando to take out the nonlinear piece and then analyze the linear operation. So this is the exact nonlinear forcing, and this is what Lando recovered as the nonlinear forcing, and of course there's nothing recovered from DMD for the nonlinear piece. So you can see that you do very well. So you can compare this and this, hoping that looks good, and this and this. You're asking DMD to do something that it's designed to do. So that looked promising on these sets of equations. I'm going to show you one more set of results here. So what about prediction? So if we've now learned linear and nonlinear operators, or something about those terms, can we now predict moving forward? So we did this on the Lorentz system. On the left is the true representation. So this is the training situation, training data set. This is our test and prediction, so that's the truth. These are what you get with the linear kernel in Lando, the Gaussian kernel, and the quadratic kernel. So remember I told you that the Gaussian was sort of generally the workhorse, and does pretty well. you can compare exactly how well it does here in terms of the eigenvalues. And you can see if you look at these two that we're very, very close in this case with the quadratic, and it's not bad with the Gaussian, I would assume that we didn't know before. So we're able to predict forward reasonably well for these simplified systems. So in the terms of revealing warts and all, we're trying to apply this now to minimal unit turbulence, and the conditioning on the Lando is actually pretty tricky. So we're trying to see if we can figure out how to do that for the higher dimensional or the turbulent scenarios. Yep.
These are the eigenvalues. What operator exactly?
So this is the linear. Let me get this right. So this is what one would have from the Lorentz system if we wrote it in that form before. Right?
Otherwise, this is purely Kelvin model.
Yeah. So that's right. So we are looking at. I mean, the best way to perhaps to say it is if we just look at this trajectory over the time horizon we're looking at here, that's what's happening, and this is what we'll be producing based on this particular way of learning it. Yeah.
How long is this time horizon?
Oh, how long is this time horizon? I wish we could remember the answer to that. Hold on, because if I wasn't jet lagged, I knew I was going to forget this, so I left the paper up. You see it? I can't see it. I think it's important to give you that number, so here we go. Where's that data? I'm not seeing that right now, but it's reflected here in terms of the length of that trajectory. I can dig out that number for you later. I'm sorry, I don't remember the training. It is dependent, right, on the training and on how far out you're looking, but I didn't put up that statistic to show you, so my apologies. Okay, so I'm about 40 minutes in, so summary so far. So I've told you this way that we're interested in looking at these systems. We're interested in moving beyond the linear representation. So explained the resolvent analysis. I've shown you how we are able to approximate that resolvent if we didn't know the equations, the governing equation. So we learned the linear resolvent, told you about physics-informed variation on DMD, and then how to learn when we separate out the linear and nonlinear disambiguate linear and nonlinear terms. So we're forcing it into this particular learning structure. So with my remaining time, I want to tell you why, or a little bit about why we're so keen on this approach. Here, I want to talk about learning the nonlinear interactions is probably key. We're just going to quantify them. This is probably not quite the right title. So here is what the forcing term looks like, that quadratic information there. In this resolvent framework, in this discrete setting, we can isolate contributions from individual pairs of scales. So at any kx, kz, and omega, k3, the forcing is governed by resonant interactions, so k1 plus k2 equal to k3, and working through this expression here. So in order to get at f, we need to run through all resonant contributions here, and we need to have, put another way, we need to think of the u interacting, u dot grad u, and then the other way around too. So here's the resonant interactions that we're looking at. So what we're going to do is use a DNS and channel flow and actually start to quantify this and see if we can see any patterns. And this kind of dovetails a little bit to what Prof was saying about low order modeling versus low fidelity modeling. We want to see if we can see this low order way of thinking about things inform anything about the low fidelity. So if we run through this and we want to think about what's going on even at one scale, we've got many, many dimensions. So what I'm going to show you is the projection, let's go to the right. So here for two scales, here's the contribution to the forcing relative to the full forcing of that case. Okay, and then I'm going to show you integrated over y and summed over kz and omega. This is going to be a 6-dimensional space in y. So perhaps easier if I show you the results. So, where are my labels? Yeah, here we go. So this is kx1 and this is kx2, and that's important because of the ordering here. I'll talk to that in a moment. So on a diagonal line, the interactions from this side and that side are exciting this given kx2. So along this line are all interactions exciting a given kx2 and so on all the way over here. So from minus plus what's contained in our data. The color is on a log scale, but if we zoom in on this white box here, you can see what you can see in the main image, which is a very strong set of interactions on this horizontal line, so it runs all the way across this kx2, and that there's not too much else going on outside that. Now you can see a bit more in the log scale. You can see that there's also some vertical line there. If you look really closely, a little bit of activity on that diagonal. In the diagonal, of course, will be the interaction of the mode with its quantum plus 1.7 minus. So what's going on? Well, this integrated version, it hides some stuff, but it tells us something pretty interesting. The first thing is that the nonlinear term is dominated by interactions between something that is long, the kx, very low in this first term, and kx can be anything within this second. So the u.grad is important, and then this one is not so preferred, not so preferred. So things along here are important. Things down here are kind of important, but not so strong, and that makes sense because anything that is long in the streamline direction tends to be tall, and so any kind of gradient tends to be low as well. So the gradient is strong when associated with smaller scale things. And then the last one, as I said, is that diagonal. What I'm showing here on the right is a collection or a schematic of what is actually simulated in quasi-linear type model. So let me decompress. So if in a quasi-linear model, if I basically linearize around the mean that now has things with kx0 embedded in the mean, and I limit my interactions to nonlinear interactions to only feed that mean, so that means, I didn't put the triad interaction, the permitted triad interaction. But basically it means that any interactions with the kx0, the quasi-linear piece, are permitted. Any small scale to small scale are not permitted. So quasi-linear admits exactly these green patterns that are consistent with what we saw in the data. So I'll draw attention to the fact that this is the a posteriori calculation of what was in the DMS, and QL is simulating this reduced system, but allowing for these interactions. So we were interested to see, say at lunchtime, that I haven't seen this characterized before, but perhaps this is a way to, another way, there are other ways to justify the QL assumption that it seems to hold, except one could maybe even make a further restriction, say that this vertical green line is much less important than this one, or that one. Now, blue here is what happens if we go to a generalized quasi-linear system. So we now resolve maybe the fundamental, or we start to increase the number of large scales that we resolve, and we account for fully in the nonlinear interaction. And so now, certainly in the horizontal direction, you can see we're starting to emit these shady regions that show that there's something of non-significant magnitude present. There's some interesting gaps. The red ones are interactions that are never captured as you go up in GQL. As you increase the modes that you are allowed to resolve, eventually you recover in a non-straightforward way. So all this is to say, by thinking about it in this spatio-temporal setting of the spatio-temporal setting inspired by the Resolvent, we get to see some pretty interesting things that maybe inform some low fidelity models. So again, this is from DNS, not from a QL system, but also this is just a quantification of the contribution to the forcing. And in order to see what actually does the damage, we'd have to run that through the resolvent. This is not doing Helmholtz decomposition, so this is quantifying what contributes to the magnitude of the forcing, not what contributes to the magnitude of the response. So that's the next thing that we need to do. Jump over the resolvent version of that just in the last few minutes to show one thing that we've been looking at, trying to use this type of approach for now. So we would like to be able to run some real-time estimation in the lab, again with a channel flow. And the idea here is to have multiple PID planes, where the multiple is associated with how many cameras and lasers we're able to purchase. But for the moment, we're going to work with a minimal flow unit. So we're going to use that to provide the data and see how quickly we can get estimates associated with where the PID planes will be. But the interesting thing is one can do this by clever polarization of the laser sheets, and then both the hardware and the software for PID is getting to the point that, at least for reasonable Reynolds numbers in the lab, this is something that might actually be able to be done real time. So again, we're going to use our real data, not from the lab this time, from a minimal flow unit. We're going to assume a number of sensor planes. This is showing the output from the minimal flow unit in terms of the RMS, U, V, W. So by using the DNS, of course, we're in the zero noise limit. We can measure whatever we want. We're truly periodic. And I should say we're going to compare with the full field. This is the work of Raoul. So we tried various ways to think about doing this, ranging from naive to sophisticated with associated different costs. So what I should have mentioned is all of the linear resolvent pieces that I've shown thus far are tractable on a laptop, so very, very trivial type computation. So the goal here is to have some training data. I'm going to show you this resolvent-based estimation approach, which is based on these two tables. Here. But we did these other ways, and one is without forcing color, and one is based on. So you can think about this as ranging from knowing nothing about the flow other than the resolvent, and weighting things by the singular values, to knowing everything about the flow because you've got the S-part representation. In the middle is the resolvent-based estimation. And so we complicated walk through what we do, but we take a training set. So we split our particular data set in half, training and testing, and we formulate the statistics. We are training, we work out our coefficients over here, and then as we move into the testing time, we're using a sliding BFT, sliding window, so that we can check our or find our coefficients. And I should say that we're tackling here only 5% of the Fourier modes, 5% of the Fourier modes, which hold about 90% of the energy in the flow. So I'll show you quickly the results. So in this data, so this is distance from the wall, and this is the U in red, V in green, and blue in W. The dashed lines are the full information, so this iteration, and the solid lines are what we get from our estimation. One more thing to tell you is that we're going to look at sensor planes as shown by these vertical lines, and if this is shaded in gray, it means that we were not using those higher readings. So this one is we only have information up to 14 in Y+, here only up to 56, here only up to 100. That's correct, but we only use this number of planes. So what do we see? We see that we do reasonably well. So if we look at the error, we're doing bang on everywhere we have a sensor plane, and we deviate away from the plane quite extremely. The error is quite large away from that, but it gets better. It gets better as we go up to having information up to 50%, so it's the Now, is this really, truly real time? So Rahul ran some numbers, and it's certainly a facility that we could construct based on how fast we do this. So he has the sliding DFT, he has some blockwise inversion that makes things simpler. And of course, we can run this in parallel as well. So it's pretty close to something that we could set up in the lab, and that's in the future in terms of trying to get a big enough channel to run slowly enough and see if we can do this in anger with a non-periodic channel with noise and with, of course, with the processing time in here as well. So with that, let me wind up. So I've shoehorned us into thinking about this way that I like to think about turbulent flows. I've told you about an operator-driven approach for the nonlinear equation, so the resolvent analysis, and the important data-driven connection to SPOD. I've told you about ways to learn that resolvent operator if you didn't know it a priori, and so one of the applications we're thinking about there is maybe plasma physics, where we don't even know what the important operator would be. We've talked about some improvements to that approach that allow us to think about non-linearity, and so Lando separates out the linear and the non-linear effects within that model and allows us to both learn that linear operator but also take a look at some aspects of the non-linearity. And so I hope you'll see this as a summary of or an introduction to a particular physics-informed approach with application that hopefully is not limited to just modeling turbulence. So, thank you. I think I probably should have bribed everybody with a coffee. It's tough to be at the end of day one. Mm-hmm. Yeah. Yeah. So we basically build the SPOD approach. So you build, sorry, but I'll let you ask the question.
No.
Okay, so we use the resolvent-based estimation approach to say we're going to observe at certain y's, and from that we can estimate what the full SFF would be. We say what should the full SFF be, and so then we follow that bold. We follow this bold line here. That's the method that we're going to use here. So now we are going to calibrate, work out our weights real time in this sliding window here, and we use that to go back through the inverse Fourier transform to get our physical domain.
So what you're learning is the linear transfer function, or you're learning the closure of the...
So the closure bit comes from the top, and then we update basically in the testing data. All right, so the top line in the training bit, we're learning the RDE version of what is going on, and then we are saying we're going to apply this, but we're going to allow for the temporal variation of that going on. But we do this mode by mode, so that's kind of key. So we run this for a fixed number of modes. So, we can do it for more modes in parallel, but that's not the cause of these errors. The cause of these errors is the way that we're learning and the fact that we don't have enough information. So first of all, we don't have enough information in terms of the number of planes. Second of all, this is non-causal because we're in the frequency domain. And so the subject, first of all, it's not causal, and second of all, the subject of the DFT losses. But in terms of what's going on at the planes, we actually do pretty well. This is minimal flow, sorry, how 180, and it came to that. It's just really because we were trying to see if we can do this. So we just about couldn't for that. We could try at higher rate.
Can you please explain entirely that is it like constraints, geometric constraints, or also some sort of conservation?
Yeah. So I mean, the examples that there's a lot of examples you can think about from outside of this fluid, but you can think about if you've got a tri-diagonal structure or if it's got another triangle. If you know what's going to be in your A matrix, then you can put that as a constraint. So in the example of the channel, we've got the shift invariant, so you can put that in as doing the DMD subject of that constraint. So Peter did a really nice job of explaining how this is related to the Kruski's problem, and there's a mathematical history to this. So it's really applying that to the DMD problem rather than discovering that this structure is important or can be used. All right, 529, 57, 58, 59. Thank you.